Okay, so now we'll talk about finding volume using the shell method. Now we've already spoken about the disk method, and with the disk method, we look at our horizontal, or sorry, we look at our axis of revolution, and when we draw a representative rectangle for some plane region, we would draw a representative rectangle so that the height of that rectangle were perpendicular to the axis of revolution. That's a distinction here. In this case, we're going to draw our representative rectangle so its height is actually parallel to the axis of revolution. This would be the representative rectangle here. And notice this representative rectangle has a height, the h is parallel to the axis of revolution, which is also horizontal. So when we do that, when we revolve such a representative rectangle about an axis of revolution, we create a shell or a tube. And we're going to basically take the volume of a lot of these tubes, very small tubes, and add them up to get the volume of a solid of revolution. So the main point of this is how to choose our representative rectangle. Remember, that's the most important thing with the disk method, the washer method, and the shell method. So in this case, our representative rectangle to represent this blue plane region is going to be this rectangle here, where this is going to be the axis of revolution. So the height of the rectangle, hy, which is going to be written as a function of y, hy has to be parallel to the axis of revolution. And py is the average radius of our shell. So py is basically the distance from the axis of revolution to the midpoint of the width, or delta y, of our representative rectangle. The width might be delta y or delta x, depending on whether the width of the rectangle is delta y, or a change in y, or delta x, a change in x. We will be integrating with respect to the y or x axis. Um, so let's take a look here. So the volume of a solid of revolution can be found this way. When we have a horizontal axis of revolution, the width of our rectangle is actually a change in y. So that's, if the change in y is small, we call it dy, and we integrate with respect to y. So you see, if it's a horizontal axis of revolution, we integrate with respect to y. And if it's a vertical axis of revolution, the width of my rectangle now is actually a change in x from this x value to this x value. And that change in x, if it's small enough, we call it dx, the little differential x. And we integrate with respect to x. If you're integrating with respect to x, all your functions have to be functions of x. If you're integrating with respect to y, all your functions have to be functions of y. And not only that, the limits of integration also have to be in terms of y here, and the limits of integration a and b also have to be in terms of x here. So let's take a look at an example. All right. So we have these directions. Use the disk or shell method to find the volume of the solid generated by revolving the region bounded by the graph of the equations about each given line. So we have first the line y equals 10 over x squared, which is this function here, which I got from the TI 83 calculator. I also have y equals 0, which is the x-axis. No need to draw that. It's already drawn there. I have x equals 1, which is this vertical line here. You can't really draw that vertical line in the TI-83 calculator because it's not a function. But I just added that line in, drawing it in. And x equals 5, well, we have x equals 1, 2, 3, 4, 5. So the end of this graph to the right is where the region would end. And this point up here, just to make note, that point is what you get if you plug in the x value of 1 into the function. Is the point 1 for x, 10 over 1 squared is 10, so that's 10 for y. So that point at the very top there is the point 1 comma 10. So the x values range from 1 to 5, and the y values range from 0 to 10 for this region, and I'll shade in the region here. This is the region that we're talking about. We're looking at finding the volume of a solid generated by revolving this region that I'm shading blue about some axis. And the first axis of revolution that we're going to look at is the x-axis. So what if we take this thing and we revolve it about the x-axis? Well, since that's a horizontal axis, I want to draw a representative rectangle that's also horizontal. So my representative rectangle is going to be horizontal. And once I have that representative rectangle drawn, I need to find my PY, which is the distance from the axis of revolution to the midpoint of the width of the rectangle. That's going to be PY. And HY is the height of the rectangle. So HY is the height of the rectangle. And I know I'm doing it in terms of y because I'm going to be integrating along the y-axis because that's where the width of my rectangle or delta y is. Okay, so now I need to identify py and hy, what they actually are. I have them labeled here so that I can use the integral above, this integral, to calculate the volume. So let's see. Let's see what we have here. Well, this is not a function of y. This is a function of x. This equation gives me y as a function of x. I'm going to rewrite the equation because I want to get the x values as a function of y. So if I have y equals 10 over x squared, and I rearrange it here, I get x squared equals 10 over y. And then I take the square root, and I should get both the principal square root and the negative square root. But since I'm looking at the right side of the y-axis where x is positive, I know that this x has to be the positive square root. So that's 10 over y. So now here I have my x values as a function of my y. And up here I can get y values as a function of x. All right, well, let's see. Let's take a look at what py and hy could be. Well, py is just the y value of any point. So the y value of this point right here, actually. And that y value is just y. So py is just the y value. The distance from the axis of revolution to the middle of the width here is just the y value of the midpoint of the width. And that's in terms of y, so that's perfect. And hy, well, hy is this distance here. And if I take a look at it, that hy there is actually this x value here, this x value, minus this x value, which is 1. This x value over here is actually the x value of the point on the function, or this x value, right? And this x value over here is always 1. So my hy is actually going to be the x value, or the square root of 10 over y, minus 1. Minus 1. So this is how I'm going to set up my integral. My integral is going to be set up this way. Just the volume is going to be equal to 2 pi, and then I'm going to take y from c to d, y from c to d, and py times hy dy. So let's see. Integrating with respect to y, integrating with respect to y, and y goes from 0, that's where my plane region begins, to 10, that's where my plane region ends. So y goes from 0 to 10, and it has to be py hy, or 2 pi. I forgot the 2 pi. 2 pi. and then it's going to be py, which is just y, times hy, which is the square root of 10 over y minus 1. And we're integrating this with respect to y. So it turns out that the volume here, if I do this integral, I distribute the y, and I do this integral, I find out that the volume here is actually equal to 2 pi, and the integral gives us 50 over 3, so I get 100 pi over 3. And that would be the volume of that solid. Now, the next thing I want to look at is what we get if we revolve this region around the y-axis. So once again, is this region on the inside here? Is this region that I previously had colored in blue? And I want to revolve it now about the y-axis. So in this case, this is slightly different. In this case, I'm revolving about the y-axis. So when I make my little uh, representative rectangle for this region, it's going to be parallel to the y-axis, or it's going to be like this. The height is going to be vertical. So the width is horizontal, so I'm actually integrating with respect to x here. And let's identify those pieces, okay? Well, the first thing is the distance from the axis of revolution to the midpoint of the width is actually, looks like just the x value here. So it turns out that my px is actually just the x value. Px is equal to x. Now let's take a look at this one, which is the height, the h of x. And remember, this has to be in terms of x because we're integrating with respect to x. And the height just seems to be, well, the height of this rectangle just seems to be the height of this function, which we know that this function is the square root of, no, actually, that's the function as a function of x. As a function of y, this thing is really 10 over x, or sorry, as a function of x, this thing is really 10 over x squared, the original. Because I'm doing everything in terms of x, I don't have to use this one over here, which is in terms of, which has x in terms of y. I'm using this one over here, which has y in terms of x, a function of x. So there I have my px and my hx. And the only thing left to do is set up the integral. But notice here, x doesn't go from 0 to 10 like y did. X goes from 1 to 5. And I have to show that as I set up my integral. So my integral, where x is running from 1 to 5, is going to be, well, and I forgot the 2 pi here also. So 2 pi times the integral from 1 to 5 of px, which is x, times hx, which is 10 over x squared, times or dx. So I'm taking this integral here. Let's see what comes out of it. Well, we have the 2 pi, and I can also bring out that 10. So actually, I can write this as 20 pi, 20 pi times the integral from 1 to 5. And that looks like when the x cancels with one of these x's, 1 over x dx. Well, the integral of 1 over x dx, well, that's going to give us 20 pi, and the integral of 1 over x dx is going to be the natural log of the absolute value of x from 1 to 5. I'm going to plug those numbers in. So I'm going to get 20 pi times the natural log of the absolute value of 5 minus the natural log of 1, which simplifies to 20 pi times the natural log of 5. So 20 pi times the natural log of 5 is the final answer there. All right, now the last one I want to do is the line y equals 10. So for the line y equals 10, well, that's this line up top here. And once again, we're revolving around a horizontal axis of revolution. So when I draw my representative rectangle, I want to draw it so that its height is horizontal. So here's my representative rectangle. The width, or the axis I'm going to integrate along, is vertical. So let's see here. I'm going to make, I'm going to look at py, which is the distance from the axis of revolution to the midpoint of the width of the representative rectangle, and that is going to be a function of y, py, because I'm integrating with respect to y. And the height, or this number here, is going to be the h of y, both functions of y. And let's see if I can identify those. Well, remember that the x values for this function, this curve, are the square root of 10 over y. And let's see. So for py, which is the distance here, for py, it seems to me like this distance is really the difference between 10, which is this line y equals 10, and the y value here, or the distance from the x-axis to where we are here. So that py is going to be 10 minus y, the y value here, this height here. Or sorry, this is the y value here, and this is 10. If you subtract away the bottom half, you only get this distance here, py. And then we have hy. Well, hy seems to be the difference between the x value on the function here and the x value 1, x equals 1. This is the vertical line, x equals 1. So that is the x value of the function, which is the square root of 10 over y minus 1. So there I have my py and my hy. And since I'm integrating with respect to y, I'm going from 0 to 10. So let's see here. We're going to integrate now. Let's extend this a little bit. We're going from 0 to 10. And we're integrating, well, we can't, I keep forgetting the 2 pi, don't I? Don't you forget the 2 pi. So 2 pi, and it's going to be py, which is 10 minus y, times hy, which is the square root of 10 over y minus 1 dy. So this is the integral that we would have to calculate in order to find this volume. Let's go ahead and do that. Okay, so this integral leads to, let's see, we have 2 pi times 250 over 3, which is 500 pi over 3. So the volume of the solid of revolution here, 500 pi over 3. All right, so that ends our lecture on the shell method. So have fun.